Well, welcome to Chapter 2. You have successfully made it through Chapter 1. Hopefully your test scores will show me that you did pay attention. Now we're moving on to Chapter 2, which is going to be fairly short. We will have 4 video lessons and then we will have a test. Our topic today is modeling distributions of data. And today we will specifically be talking about percentiles, cumulative relative frequency charts, or graphs, and z-scores. Percentile. A percentile we hear all the time. You guys get standardized test things back and they say you were in the 85th percentile. But what does the percentile mean? What is a percentile? Well, what we would say the pth percentile of a distribution is the value with p% of observations less than it. In other words, if you score in the 85th percentile, then there are 85% of observations who scored less than you. Let's look at what this looks like. Let's see what this looks like. Let me move this over a little bit here. All right. So first of all, this guy right here, this is my man, Ian. Just thought you might want to know that. Oh, I don't want to mess up his face, so we'll just, we will give him another arrow here. Woo, Ian Desmond, my favorite. All right, so we're going to do a baseball example with the percentile thing. The data below shows the number of wins for each of the 30 Major League Baseball teams in the year 2009. And I've got all of these little numbers here. Now I've put them in order. I put them into my handy dandy little calculator, and I put them in order. And what I want us to do is to determine the percentiles for these teams. The Rockies with 92 wins, the Yankees with 103 wins, and the Royals and Indians, who both had 65 wins. Well, we know there are 30 teams. And in order to find a percentile, we just figure out where the number is, divide it by the total. So in other words, we're looking for the number 92. We're looking for the number 92. So we see 92 is here. I'm going to circle that in red. And I want to know which number is that in this distribution. So I'm simply going to count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So there are 24 numbers below 92. So that means the 92 is greater than 24 of the teams. So for the Rockies, to find the percentile, I'm going to take 24, which is the places below 92, and divide it by 30, the total number of teams. And I get 0.80, which is the 80th percentile. Because they have 80% of the teams had fewer wins than they did. It was a good year for the Rockies. Not so much this year, I don't think. All right, let's look at the next one, the Yankees. Now, the Yankees are a pretty easy team to look at because we see in this year, 2009, clearly not 2014, that the Yankees had 103 wins. So we want to look at how many pieces of data are less than this one. Well, we know that that's the top number. That's number 30, so there are 29 below it out of 30. And that is 0.97, or the 97th percentile, because 97% of the teams won fewer games than the Yankees. And I know what you're saying, but Mrs. Byrie, the Yankees won the most. You're right. But we don't say 100th percentile. They're not in the 100th percentile. And the definition we're going to use, we're never going to use 100th percentile. If you are the top team, then you are going to look at below all the teams below you. Now, if we wanted to be the 99th percentile, we'd need to have 100 pieces of data, and the Yankees would be at the top. We get 97th percentile because, remember, we're looking at 29 out of 30. All right, and then the last one is kind of two parts. The Royals and the Indians who both have 65 wins. Well, we want to see where's 65. Right here. So 65 was, there's only 3 below. So the Royals and Indians, who have vastly improved since this year, had 3 out of 30, which is 0.10, which is the 10th percentile. So they fell within the 10th percentile. 90% of the team scored one more than they did. So percentile is not, if you get something back that says, oh, you scored a 97%. No, you were in the 97th percentile. That means 97% of the population did worse than you did. Percentiles can be very nice to look at in comparison to other things. So what about this 100th percentile thing? Well, sometimes people define the pth percentile as the value with p percent of observations that are less than or equal to. So in other words, this would allow someone to score in the 100th percentile. But we will not use this definition. So I'm sorry, children, but none of you will ever be able to be in the 100th percentile. All right, now we're going to talk about cumulative relative frequency graphs. Wow, that is a lot of words. Cumulative, meaning it's continuing to build. Relative frequency always refers to putting things into percent. So there's a little Mrs. Byrie, bonus Byrie hint. Relative frequency is always referring to percent. Putting data into percent. And a cumulative relative frequency graph is just going to take those percents and build one on top of another. So, a cumulative relative frequency graph, and I'm just going to tell you, I'm not going to write this out all the time, so I'm going to say cumulative relative frequency graph. Okay? CRFG, that's what I mean. It's one of the most common graphs used in statistics, and it is a nice one because it gives us a picture of a curve which graphically shows the cumulative relative frequency of a distribution. Okay, so again, remember I said relative frequency is referring to percents. To find the relative frequency, we use the frequency and divide it by the total number of observations in order to get what? That's right, a percent. All right, so right here, I've got a little question for us to work on. The ages of the first 44 U.S. presidents and when they were inaugurated. So we've got our frequency counts here. You see our frequencies. Remember, our frequencies are just like tallies. We're just keeping tally marks, or counting how many of them were inaugurated in their early 50s. Well, 13. So in order to find the relative frequency, we take 2, that's our frequency, and divide it by the total. Well, what's the total? 44, if you were paying attention. So 2 divided by 44 gives us 4.5%. And if we do 7 divided by 44, we get 15.9%. 13 divided by 44 is 29.5%. 12 divided by 44 is 27.3%. 7 divided by 44 is 15.9% again. And 3 divided by 44 is 6.8%. So this is the relative frequency. We've just taken the frequency and turned it to relative frequency. Now, we want the cumulative relative frequency. The cumulative frequency. So we're going to take the frequency and we're going to start with 2. And then we see here we've got 7 more. So we're going to add the 2 plus the 7, so we get 9. Then we're going to add the 9 plus the 13 here, and we get 22. So in other words, we are accumulating. We're not just saying how much are in each group. We're saying, oh, look, there are 22 who are less than 55 years old. It allows us to pick a point and then to look at what's behind it. So again, add 12 to 22, you get 34. Add 7 to 34, you get 41. And add 3 to 41, you get 44. And if you don't have 44, you added wrong because there's only 44 presidents we're representing. Now, the same thing can be done with the relative frequency. So in order to find the cumulative relative frequency, we are going to take the 4.5% and we're going to add it to 15.9%. So we get 20.5. The other way you can do this is by doing 9 over 44. And then you could see 22 over 44, which is 50% for those of you who are not paying attention. 34 over 44 would be 77.3%. 41 over 44 is 93.2%. And thank goodness that 44 over 44 is 100%. Now this is the cumulative relative frequency. And we can graph this in a chart in order to see how things are growing. At what rate is most of the growth? In other words, we'll be able to look at this and really see the peaks of people who and the ages that they were president. All right, so to make a cumulative relative frequency graph, that's a lot of words. We're going to plot the points corresponding to the CRFG in each class at the smallest value in the next class. I'll show what that means. In other words, we're going to plot 4.5% at 45 years because that shows that 4.5 were inaugurated before 45. So I'm first going to start off by labeling my graphs. Ages of U.S. Pres at inauguration. Down here, I'm going to have the ranges in age ranges. And on this side, I will have the percent. Whoops, what happened? Okay, percent. All right, so I'm going to start off here at 40 because that's our lowest that we went. 45, 50, 55, 60, 65, and 70. And then we know we have 100% that we'll end up with. So, oh goodness, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So this is 100%, 80, 60, 40, 20, and you can fill in the rest on that. All right, so now we're going to just literally make dots where we're starting at, where each age is. So you're going to have to flip back and forth to on your notes that you have in front of you. I'm just going to graph because I have my notes in front of me. Now I know at age 40 there were no presidents at age 40, so I'm going to start this down here at 0. Now before the age of 45, we had 2 U.S. presidents inaugurated, which was just 4.5%, so not very much. And then before the age of 50, we had 20.5% of the U.S. presidents were inaugurated before they were 50. Before the age of 55, we see that we had 50% of them inaugurated. Before the age of 60, we had 77%, somewhere right about in here. Before the age of 65, we're all the way up at 93, right about there. And by age 70, we had all of our presidents inaugurated by that age. Now we're just going to connect these dots. And we have built a cumulative relative frequency graph. And it allows us to see that a majority of our presidents looks like they were inaugurated between 50 and really 65. Things start kind of flattening out here they're flat, and here they're pretty slow as well. We have rapid numbers here. So here's a picture that's much nicer than the one that I just drew for you of the same graph. And what I want to know is, how do we interpret this? Well, the graph grows gradually because few men became presidents before in their 40s. The graph goes up quickly for men in the 50s and 60s, and then begins to taper off. So we can tell in this information, with this original chart, we can tell quite a bit of information with regards to the president's ages. Sorry, I'm so sorry. So here, we want to use the CRFG to answer a couple of questions, and we can do this just by looking at our graph. So we want to start off to say, okay, was Obama, who was inaugurated at the age of 47, was he unusually young? Well, the nice thing about these is that we can just use the graph to kind of, let's have some different color. Let's have purple. Okay. We're going to take age 47, which is approximately right here. And I'm going to find the spot on the dot that corresponds to 47. And then I'm going to go this way and figure out an approximate age for a percentage of presidents who were younger than President Obama. Well, it turns out that about 11% of presidents were younger than President Obama. So this does indicate, not Obama. This indicates that he was unusually young. Okay. Now, part B, I want us to estimate and interpret the 65th percentile of the distribution. All right, the 65th percentile, I'm going to go up here to 65. That's 70, so I'm going to guess 65 is right about there. And I'm going to go across here. Now, I understand it would be better if I actually had a ruler, and I don't. And I end up right about here, which I'm going to say looks like a 58 to me. So that means that the 65th percentile corresponds to age 58. So 65% of U.S. presidents were younger than 58 at the age of inauguration. So do I need to write that down? 65% of U.S. presidents were younger than 58 at their inauguration. Okay, that's how we use percentiles and cumulative relative frequency graphs, which you cannot say 5 times at once. Okay, clearly it's been a long day. You can't say 5 times quickly at once. Oh my. Okay, really quickly, I don't think I should have to tell you this, but I'm assuming that by now you may have figured out some relationships between percentiles and quartiles. So I'm hoping that you guys are all brilliant enough to realize that quartile 1 represents the 25th Okay, my machine is weirding out, so please, I apologize for that. Is the 25th percentile. The median would represent what? Oh, that's right, the 50th percentile. You guys are so smart. And quartile 3, I hope you understand, represents the 75th percentile. Mrs. Byrie, it all goes together. Why, yes, it does. I'm so glad you noticed. Now, the last thing we're going to talk about is measuring position. We can describe an observation's location in a distribution by telling how many standard deviations above or below the mean the observation is. Now, when we're looking at standard deviations, sometimes we've got all these crazy standard deviations that are, how many points above, below. It gets a little crazy. We can convert observations from their original measures to standard units. And this is called standardization. Shocking, isn't it? We like to standardize data. Now, one of the ways that we standardize data is to use something called a z-score. Boys and girls, you must learn the z-score. You must make friends with the z-score. You must memorize the z-score. The z-score will be with you throughout the end of statistics this year. Now, the z-score simply is a number that tells how many standard deviations away from the mean an observation falls and in what direction, above or below. The great thing about the z-score, or the standardized value, is it has a very simple formula, and yes, you need to memorize it. It is z equals whatever the observation is, whatever the value is you're looking at, minus x bar, which is the mean, divided by, yes, our friend, standard deviation. Now remember, this is the formula for sample standard deviation. Formula for samples. We'll get into populations at another time. It's basically the same thing, only we use a different representation for mean and standard deviation in a population. All right. So here are some grades from Mrs. Byrie's first AP statistics test, and they have the following output in something called Minitab. Now you're going to see Minitab statistics pictures quite a bit. This is really literally a screenshot from Minitab. We do not have Minitab on our computers here at school, and we're not going to get it. It's not that important, but it is important that you are able to read a Minitab output. So you can see descriptive statistics. It says test 1 scores, and then it tells you the variable and the scores. And then this is just our major topics that we use. We have the number, the mean, the median. Trimmed mean we'll get into later. Trimmed mean means we found the mean without the outliers. That's all it means. Standard deviation, the standard estimate mean, which we're not going to use right now. Minimum, maximum, quartile 1, quartile 3. So it's pretty much a number summary, only instead of it being by hand or on your calculator, it's just in a computer package. Now we want to find the z-scores for these students and interpret the value in context. So Peach scored a 93. If you haven't figured this out, these aren't real scores, okay? Don't panic. I don't think that the median was an 80 on that test, although I haven't graded it, so I couldn't tell you. Okay, so Peach gets a 93. So remember, z-score is equal to x minus x bar over standard deviation. So Peach has a 93 minus my mean, which is an 80, over my standard deviation, which is 6.07. And if we use our handy dandy calculator, we would find that that is 2.14. and it's positive. So Peach scored 2.14 standard deviations above the mean. Peach is pretty smart. Now let's look at Yoshi. Yoshi scored a 72, minus the mean of 80. Clearly we can already see that he is not as smart as the average person. Divided, or maybe not on this test, divided by the standard deviation. And when I plug all this in, I get negative 1.32. It is okay to have a negative z-value. It just indicates that it is below the mean. So negative z-value means the z-value is below the mean. I know that seems obvious, but I have to say it. So that's a negative z-value. All right, so Yoshi scored negative 1.32 standard deviations below the mean. That's as easy as it is. The entire point of standardizing scores and to put them in z-scores is so that we can standardize them across different distributions. For instance, if I taught 3 sections of statistics, I could take everyone's grades from all of the classes, regardless of what their individual classes did, and I would be able to compare them with each other. I could see how many standard deviations above or below they fell. And if you want to see that happen in your book, if you would like to look on page, I believe it's 89 and 90, you can see a little bit about Ginny's test scores in 2 classes, and you'll be able to see how you can use the z-score for comparison. We're going to do a very quick check for understanding. This is the last thing we're going to do. And we're going to figure out interpreting some z-scores. So here is a set of fairies in fairyland, and they made a dot plot of the heights they would prefer to be if they were able to grow up. The figure on the left shows the dot plot and the number summary of the height wishes of the fairies. Yes, I made this up. It's okay. I'm in a mood. All right, so we see that we have a variety of heights here, which we will probably look at something similar to this next class. And I've given you a number summary, so you don't have to do much work. Here's your standard deviation. Here's your mean. That's pretty much what we need. So let's look at poor Tinkerbell. She really, 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 really wishes that she was 65 inches tall. So we want to find and interpret her z-score. All right, so z-score is, again, x minus x bar over standard deviation. I write this out frequently so I don't forget it. So she wishes she was 65 inches tall. I'm going to subtract that from the mean, which we're noticing here is 67. And I'm going to divide it by the standard deviation of 4.29. Now, that looks to me like I'm going to get an answer. I know it's going to be negative 0.466. So what does this mean? This means that Tinkerbell's wish is 0.466 standard deviations below the mean. Mean wishes, mean fairy wishes. I don't know. That's a weird thing. What was I thinking about when I wrote this question? All right, Zarina, and in case you're wondering, yes, Zarina is a Disney fairy. Zarina wishes she was 74 inches tall. Apparently she wants to be really tall. How big a wish is that compared to the other wishes? Well, z-score again, x minus x bar over standard deviation, 74 minus 67 over 4.29 is 1.63. So Zarina's wish, telephone, hold on, no. Let me call you right back. Zarina's wish is 1.63 standard deviations or standard units You can just say standard units above the mean Harry wishes. Sorry, that was Noah on the phone, and I hung up on him just for you guys. I could have pushed pause, but did I do that? No! All right, our last question is a little bit different. So this time I know that James is a pirate, and he's a member of the Pirate Plank Diving Team. The average height of the pirates on the team is 76 inches. James's height translates to a z-score of negative 0.85 in the team's height distribution. What is the standard deviation of the Pirate Plank Diving Team members' heights? Well, I'm assuming that most of you could figure this out, but I'm going to help you a little bit. We know that the equation for z-score is z equals x minus x bar over standard deviation. So, what do we know? We know that z-score, in this case, is negative 0.85. We know x bar, or the average, is 76. And I guess I didn't tell you up here, but James's height, I should put that in here. James's height is 74. Wow, I must have missed that. Important knowledge. And x is 74. So what are we going to do? We're just going to plug it in and solve for standard deviation. So negative 0.85 equals 74 minus 76 over standard deviation. So I'm going to have, I'm going to just multiply both sides by the standard deviation so I can get rid of that. So the standard deviation times negative 0.85 is equal to negative 2. Divide by negative 0.85. And I get 2.35, I think. I can't read my own writing. 2.35. So the standard deviation of the Pirate Plank Diving Team is 2.35. And I'm assuming these guys are inches. We always want to make sure when we're talking about standard deviation, we give units. All right, I hope you've enjoyed this instructional video on percentiles, cumulative relative frequency graphs, and z-scores. Next class, we will continue this lesson and learn how to transform data. Woohoo! See you tomorrow.